sort of Jim Hartle didn't do a big formal introduction a couple weeks ago at our colloquium, and I thought, okay, that's a good idea. You're not going to remember the dates or thesis advisors or any of that stuff. Aaron, though, started out at Case Western Reserve, where there's been a lot of great dark matter stuff has happened, and moved on to Florida and then University of Zurich, and built 2 laboratories with Laura Bautis, who's now still in Zurich. But, you know, in this game of trying to learn the second thing about the dark matter, the first thing is that astrophysics and gravity tells us it's there in space. And the second thing is to try to touch it somehow, and we'll hear about that. But it's a game where there's a lot of escalation of trying to build bigger and bigger detectors. And I used to work on one technology which was using germanium, and it was Aaron who 10 years ago convinced me, and I don't think you even knew, he didn't even know he convinced me, which is also great, okay, that in fact there was a way that would lead to more sensitivity quicker in the search for dark matter. And so Aaron is full of a lot of good ideas, and that's one of the reasons, among the many reasons we invited him was so he could come here today and tell us some of those ideas. Today it's a stab in the dark. Take it away, Aaron.
Turn to the front.
Oh, that'd be great, yeah.
Yes.
Well, it's a pleasure to be. Oh, it's really intimate now. Dark. Yeah, exactly. Yeah. So I've been to Santa Barbara twice before, and I realized when I was coming down here that the other 2 times were also in the month of February, and I didn't even notice it because it feels like kind of spring here. So it's really kind of nice to come down here. All right, so it's just kind of difficult to give a talk on dark matter here because we have a group that does dark matter, but I also understand that this is a department-wide colloquium, and I know, for example, when I go to a colloquium on condensed matter physics, I really appreciate it when the speaker doesn't just assume that I know what topological phases of matter are. So I'm not going to assume you really know anything about dark matter. It's going to be sort of a whirlwind tour about what we know about dark matter and how we're looking for it. So here's a screenshot from one of my favorite movies. And it's, if you may recall this scene, it's when Obi-Wan is teaching Luke about dark matter. He says, it surrounds us, it penetrates us, it binds the galaxy together. Okay, so now obviously he was not talking about dark matter, but it's kind of fun to think about, you know, he could have, because it's foreseeable that George Lucas knew about dark matter, because the origin of our understanding about dark matter is not in 1977. Our understanding about dark matter begins instead a long time ago in a galaxy cluster far, far away. And a long time ago means 1933. Okay? So let's go back to 1933. What did we know at that point? Well, we knew, this is a long-standing question, we knew that the Milky Way was one galaxy among many. We knew also that all other galaxies except one are moving away from us. And then furthermore, we found out that the galaxies that are farther away from us are moving faster away from us. This is a profound discovery by Hubble. It tells us the universe is expanding. We also knew that galaxies are not just distributed randomly, they tended to be clustered in the sky. And so here's one cluster of galaxies. Every smudge here is a galaxy. This is called the Coma cluster. It's in the northern hemisphere, kind of lives near the Big Dipper. There are over 1,000 galaxies that people have identified here. So in 1933, people were still kind of trying to make sense of how fast things were going away from us. And there was a Swiss astronomer, Zwicky, who decided to ask, well, instead of just wondering about how things are moving away from us, let's ask about what's the dynamics of a cluster like this? How are they moving with respect to each other? And he was led to ask a really simple question, which is, how do I estimate the mass of the galaxy cluster? And it's a really simple question, but what he quickly discovered is that it has a really complicated answer. And in some sense, 85 years later, we're still trying to sort of unravel the answer to this. So let's go through what he did. He said, well, basically nobody's done this before, so he kind of had to make up a way of estimating the cluster. He said, well, I know each galaxy is radiating, I know it's emitting light, and I know that there are stars in them, so let's measure the total luminosity, L sub I, of each galaxy, and let's make the ansatz that our sun is somehow representative of a typical star in those galaxies, so let's scale those luminosities by the mass to luminosity ratio of our sun, and then we get a mass estimate from each galaxy, and then the mass of the cluster we just sum over the galaxies. Okay. Simple, kind of hand-wavy, but it's a start. But he was a good scientist, so he said, well, does it make sense? Let's ask a sanity check. Does this cluster then satisfy the virial theorem? So the virial theorem relates the average potential energy of a system to the average kinetic energy of the system. And well, if I'm calculating average kinetic energy, that's the average of v squared, so that's an RMS. And so he calculated, based on his estimate of the mass, that the relative velocities of these galaxies should have an RMS value of around 80 kilometers per second. Okay. The problem was, the measured RMS of these galaxies was over 1,000 kilometers per second. Now, it's not clear to me, there's a lot of hand-waving that went on in estimating that mass, so it's not clear to me to what degree of agreement he would have accepted, but it is clear that he did not accept this discrepancy. So he answered this question, does it satisfy the virial theorem? The answer was a resounding no. So he goes on to say that in order to make this virial theorem thing make sense, I need to add about 400 times more mass in the galaxy cluster than what I estimated. And if we take these, he says in bold, if this were true, then the surprising result would be that dark matter, he distinguishes dark matter from luminous matter, is present in much greater amounts than luminous matter. And he coins this term, dunkle Materie, this is German for dark matter. He was aware that he was only estimating the mass of the illuminating matter, the luminous matter. And I get the sense from reading the paper that he didn't actually take this seriously. He thought that there was probably some systematic uncertainty in the measurement of the velocities that led to this. And he tried to figure it out, but he really couldn't. So this is an anomaly that was long-standing, started there. Okay, let's fast forward. In the 1960s, people started to measure, not only take a spiral galaxy edge-on, not only try to measure the velocity that this galaxy is receding away from us, but they were able to distinguish that the left side of the galaxy was maybe moving a little bit faster away from us, and the right side was moving maybe a little bit slower away from us. And that indicated that the galaxy was spinning. And then a few years later, they were able to distinguish, okay, as I look from the center, I can measure the speed of the material in the spiral galaxy as a function of the separation from the center. So if there's one piece of evidence for dark matter that probably all of you have seen, it's probably this topic of rotational velocities. This led people to ask the same question about galaxies that Zwicky had about galaxy clusters, which is, can we make sense of the dynamics of the galaxy? And they were able to predict if the mass of the galaxy was correlated to what I see, then the rotational velocities of the matter, of the material, should drop off as a function of radius. Instead, they measured that it would continue to rise, in some cases flat. It's flat. So this can be explained by additional matter in the galaxy. So Vera Rubin was the person who really brought this to the fore, brought this to everyone's attention. Okay, I'm going to show you one more piece of evidence for dark matter that's kind of a different nature. I'll show you first without explanation. This is probably one of my favorite astronomical images, maybe one of two. So this is a picture, this is some galaxy clusters again. It's a type of evidence for dark matter that some people say is sort of smoking gun caliber. In fact, the authors of this paper were so confident that they titled the paper "A Direct Empirical Proof of the Existence of Dark Matter." It's really confident. So in order to explain this, I have to back up and talk about galaxy clusters some more. So Zwicky said that, well, we need more mass to explain the dynamics. And we now know that, at least to some degree, he was right. What they didn't know is that in a galaxy cluster, in between the galaxies, there's a very dilute gas of hydrogen. Actually, it's not a gas, it's a plasma. And so here's an example of a galaxy cluster. You see in optical, all the galaxies. And then in X-ray, because that's what this plasma emits, you see this big cloud. It's very dilute. You get, in a liter of volume, you get about 1 proton. But in a galaxy cluster, there's a lot of liters. So this adds up to a lot of mass. If I take all of the baryonic mass, baryonic is a term part of physics people use just to mean protons and neutrons. We are baryonic matter. if I take all the baryonic matter in a galaxy cluster, including the stars, the planets, and the dust, about 95% of it is just in this dilute gas that's between the galaxies. It's just because there's so much volume there. Okay, it's not enough to explain Zwickie's discrepancy, but it does soften the discrepancy. Okay, so earmark that. We'll come back to that. Another thing is that we found out that galaxy clusters are so massive that they can actually bend light. And this is an example of what we call gravitational lensing. So here's sort of a diagram. Here's us. There's some distant source and some very massive galaxy cluster, and the light kind of bends around it. We see multiple images of that, and they're distorted. So in this galaxy cluster image, you see that there's these streaks. Those are from a distant object that's been distorted gravitationally by this lensing cluster. Now, the thing is that because we think we understand general relativity, we can use statistical analyses on the shapes of these streaks to reconstruct not only the amount of mass that's in this lensing cluster, but also the distribution in space. Okay. Let's go back to this. This is actually two galaxy clusters, and they collided about 150 million years ago. And overlaid, this is a composite image, from the X-ray satellite Chandra is the pink. That's where the main normal matter is, the baryonic matter. And then if you ask, where is the main mass from gravitational lensing, that's the blue. Now, what's striking about this is that from the perspective of dark matter, this kind of makes sense. If dark matter is in a galaxy cluster, these two things went through each other. The dark matter is not collisional. The blobs of dark matter just passed right through each other. Maybe they were tidally disrupted. But we know hydrogen gas, or plasma, is collisional. And that got stripped off of the galaxy clusters. In fact, you can even see the shock wave there, the bow shock. Okay. Now, the other two pieces of evidence for dark matter were of the nature of strength. They were a discrepancy in the strength of the gravitational force, or a discrepancy in how mass reacts to gravitational force. But this is a very different kind, because I've got a lateral separation between the main component of matter that we know about and the point around which light is getting bent. Okay? So if I look at this from the lens of, I'm not going to believe dark matter, I'm going to believe that there's alternate theories of gravity, what this means is that here's the main mass, but things are being pulled to a point over here. So it's almost like a gravitational ventriloquism. And it's hard to understand that from an alternative theory of gravity, because this is not an extreme environment. This is not a relativistic high field situation. This is a non-relativistic collision that, even though this is very massive, these clusters are very massive, they bend light, the actual local curvature in these cases is not strong. We're not in a situation like we have two colliding black holes. So it becomes difficult to, maybe even implausible to imagine an alternative theory of gravity that would allow some mass to sort of project to another point in space, such that in that empty point in space, gravity or things would just sort of bend around that. So this is a really smoking gun piece of evidence for dark matter, because it seems the only real plausible way to understand this is that there is dark matter in here that was not collisional in here. All right, there's a lot more evidence for dark matter that I just really don't have time to get through. I'll just point something out. Formation of structure in the universe, collapse of matter into structures that we see today from the initial conditions. We need dark matter to really explain that. I talked about rotation curves. Cosmic microwave background. This is the heat left over from the Big Bang, and these are temperature variations in the sky. We learn a lot about the early universe, and from that we also learn that there was extra matter there, and that there were situations where the main mass got separated from the baryonic mass. And then gravitational lensing also tells us about the potential wells in the galaxy clusters. All right, so obviously the question next is, what is the dark matter? So the answer is, we don't have any idea. But I'll tell you what we do know. Here's what we kind of know at the moment. We know that dark matter is the cosmic energy budget. Most of it's dark energy that I'm not going to talk about. About a quarter is dark matter, and the remaining 5% is ordinary matter, I mean, protons and neutrons that we know about. Most of this is intercluster plasma, and a tiny fraction is like people. Okay. We know that the dark matter was produced cold. That means that when it decoupled from the rest of the universe, the particles were non-relativistic. We know that because that's the only way we can get structure to form into the things we see today. We know it's not baryonic. We can't explain this with the standard model of particle physics. It probably does not clump on large scales, or small scales, like planets that just aren't emitting things. We have measurements that just show that these kind of things can't account for all the dark matter. It played an important role in structure formation in the universe. And then locally, like in this room, there's about 300 proton masses of dark matter, the amount of mass equivalent to 300 protons per liter. Okay? Now we don't know how many dark matter particles there are, but that 300 protons, that much mass is on average in each liter in this room. So, but we don't know what the mass is, but we have narrowed the mass of the dark matter particle to a very specific range. We know some specific bounds on what it has to be. It's a very tight range. It's anywhere from 10 to the minus 22 eV to maybe 10 to the 19 GeV. Very specific range. So there is actually a hard cutoff here. We know the mass of the dark matter cannot be less than 10 to the minus 22 eV, because if it was, the Broglie's wavelengths of the particles would be larger than the smallest structures we see in telescopes that are dark matter dominated. 10 to the 19 GeV, that's the Planck scale. It doesn't really even make sense to talk about particles that are more massive than that. And if there was an elementary particle that was more massive than that, it was dark matter, then its de Broglie wavelength would be smaller than the Schwarzschild radius, and then it would form a black hole, and then what happens, we don't really know. So we do know that, however, below about 1 eV, we have to start packing a lot of particles into the same state, and so they have to be bosonic. And in fact, when I pack a lot of particles in the same state, and I have long wavelengths, the dark matter here will sort of just behave like a classical wave. And above a mass of 1 eV, these things will behave more like particles that we think of. So this sort of informs us about also how to do experiments that might help determine what these are. So I'm just going to tell you that for both classes, there's the most popular examples historically that people have been excited about. So in the particle dark matter world, the WIMP, the weakly interacting massive particle, its mass is probably in the range of 10 to 1,000 GeV, or would be. And this is exciting because it's related to things we don't understand about electroweak symmetry. Okay? And in the wave-like side, the most popular candidate is something called the axion. Its mass would have to be somewhere between 1 and 100 microeV. And this is related to things we don't understand about the strong nuclear interaction. Now what's exciting about this is that both of these candidates are things that could explain dark matter, so resolve anomalies on the largest scale of the universe, and they both also resolve questions about high-energy particle physics, so questions about the smallest scales of the universe. So this is a really interesting coincidence, and it's a very compelling idea. Now, I would love to talk about the axion, and I have some slides that I had to move to backup because I really just don't have time to talk about it, so I'm going to skip over axions. I'm not going to say anything more, unless you ask me and I can show you my backup slide. And we're just going to talk about this side of the color scale here. Within particle-like dark matter, there's a regime called the thermorelic range, between about 10 keV and 100 TeV. And I'll get back to what that means, well, I guess in the slide. The WIMP is a subset of that, but this is the range where a particle could have been produced thermally in the early universe, just because the universe was hot in its infancy. So, what is a thermal relic? So, in the early universe, it's very hot. Particles are being created. There's lots of collisions. Particles are being destroyed through annihilations. And there's an equilibrium for any particle species. There's an equilibrium number, concentration of that particle species. If the production rate is higher than the destruction rate, then that number density will rise, and I'm getting more particles, so the destruction rate starts to rise as well until they meet each other, and then I get this equilibrium concentration. Well, as time progresses, the temperature of the universe is decreasing. At some point, the temperature starts to get similar to the mass of the particle, and when that happens, the production rate starts to slow down, and the equilibrium number density starts to fall off, because I'm just not producing them very much. But at the same time, the universe is expanding, so the space between particles is growing. It's becoming more and more difficult for two particles to find each other and annihilate. So as this number density is dropping, it could be that the annihilation, the destruction mechanism, just shuts off. And if that happens, then I'm left with a population of this particle species. It falls out of thermal equilibrium. There's nothing to get rid of it. It's not being produced anymore. It's there. And what the important thing is what is the annihilation cross-section? If the annihilation cross-section is stronger, then of course it's going to follow this equilibrium curve further down before it falls out. We call this process freeze-out. Okay. Now notice there's no Feynman diagrams that I showed here. There's very little reliance on models. This is a very generic production process. It just says there's a creation mechanism and a destruction mechanism, and then temperature is going down and the universe is expanding. But we can try to do some calculations and figure out, okay, in order for this amount of leftover matter to account for the dark matter that we see, what is the annihilation cross-section that we need? And you come to this approximation. This side is complicated for the condensed matter people. This just means abundance of this particle. And here's the annihilation cross-section times the velocity. And we know this side of the equation. And so we can solve for sigma, the annihilation cross-section. And lo and behold, what we find is that the annihilation cross-section is characteristic of weak scale annihilations, weak couplings. And this is interesting because there's an open problem in the high energy physics community about electroweak interactions. There's a symmetry, electroweak symmetry. It gets broken at the 100 or 200 or 100 something GeV scale. It's involved with the Higgs. The natural scale for the Higgs mass is the Planck scale. The Higgs mass is 125 GeV, far below that. We don't understand why that is. Okay? So we postulate that there's new physics that we don't know about that is helping to keep the Higgs mass well below the mass it should be. And so if there's new physics needed to explain the dark matter, and there's something pointing to the fact that this new physics should have annihilation cross-sections that are weak, characteristic of the weak scale, this is exciting because maybe this is related to new physics that explains electroweak symmetry or electroweak naturalness. And so we call this the weakly interacting massive particle. And this has been around for a while, this idea. It was sort of invented at the same time Star Wars came out, 1977. And this has been considered such a beautiful explanation of two separate phenomena that people sometimes call it the Wimp miracle. So how do we try to discover this particle? There's, in general, three avenues. You can try to make, okay, SM, standard model. This means a standard model, what we know about. You can try to make this in a lab, like in a collider, smash a normal particle into another normal particle and produce two dark matter particles. You can look in like the center of a galaxy where there should be a high density of these things, and occasionally they may annihilate into standard model particles, and you can look for these things in telescopes and other types of detectors. Call it indirect detection. Or you can look for interactions